So, okay, so we'll get started with today's workshop, and I've shared the link with you, and please click on that link. And if you haven't gotten the link, I'm sharing it with you again. And this is a GitHub link that we are going to use. So any questions so far on what we're going to do in this workshop? Or if you have any questions? Okay, so if not, let's go to the. So let's go to the page. So this is what you would be seeing. It's a GitHub page, and the link is put in the chat. So you can click on that link and it should open this page for you. So once you see this page, the thing that we are going to use is a Google Colab notebook. And there's a question in the chat is, do I have to have background knowledge or info to be able to understand? So in background knowledge would be needed to some extent, but the thing that you would see is just a interactive notebook where you can just press click enter and it runs the code for you. So you can see how it's done and then you can think of modifying it, but most of the things that are required are done. So you can give it a try and see how much you can understand while you are doing it. So yeah. Okay, I hope that clarifies the thing. So, okay, so I hope you can see this screen of mine and which says GitHub. And if everyone can see it, please give me a thumbs up so that I know it's still being shared. Yes, okay. Okay, so awesome. So is everyone able to open the page, the GitHub page? Yes, okay. So I'll show you how to start with this. So click on the parsing files.ipynb. So once you click on that, you'll be taken to this thing which has the code for it. And all you need to do is click on this blue thing that you see on the top, which says open in Colab. And that's where we are going to run these things and see how we are going to parse it. So if you're on this page where it shows the parsing file INB and it shows this nice notebook, please give me a thumbs up so that I know we can start once a lot of you are on this page. So you need to go to the link that I shared with you, and this is the link again for people who did not get it. And please let me know once you are able to access this. Click on parsing files and then click on the blue thing that you see on the top, which is open in Colab. It should open you this file that you see. So do give me a thumbs up or something so that I know people are ready to work with this. So if you have any questions, please do let me know. Okay, there are a couple of thumbs up. So okay, so we'll get started with this. So the first thing that we need to do is install pymatgen. So we'll be using pymatgen as a part. Oops. Okay, so you can just say run anyway. And then to click on to run this, you can just press the play button and it'll run the code for you. So the code is already written for most of the things. So you just press the play button and it should run. So there's a question which asks, do we work with you at the same time? Yes. You can just open the book and just press play, and you can do whatever you want with this. You can write your own code in this if you're comfortable doing that, and you can execute it at the same time as me and see how it's working. And this is the interactive part of this workshop for you. So do click the first play button, which installs pymatgen, and it'll take a while to install it. It'll show the installation process. And once you see it says it's successfully installed pymatgen, something like this, you should be fine to proceed for this workshop. So as long as you see the final thing which says successfully installed, it should be okay. You will definitely see an error for this in between, but it's okay. But you should see this thing at the bottom. So if people have reached at this point, do give me a thumbs up or let me know you have reached here so that we can proceed further. One thumbs up, waiting for a couple more. So open this thing that you get from the GitHub file, open in Colab. You'll see something like this, and then click on this play button, and it should run the code. So there's one thumbs up, and I'm waiting for a couple more so that we can get started with the next part of it. So at the end, you should see an error, which is like that, but it should also say successfully installed all of this. Okay, there's one more thumbs up. So any questions so far with installation? Okay. So it'll be downloading. It'll take a while to download, but it's all done on Google's machine. So it'll be a bit quicker. You're not downloading anything for the local PC that you're working on or the laptop that you're working on. Okay, I hope it's installed, and once it's installed, we'll get the files that are needed for this, and we'll do some cleaning up of files. So just go ahead and click on this play button. It'll say it's getting you files. Okay. And if you want to look at the files that are being downloaded right now, just click on this folder like thing at the side, and you'll see that we have gotten the files that are needed, which has Gaussian and VASP. So these are the two things that we'll be working with. And once you see those files over here, just click on this thing that you see at the side. And once you're here, do let me know it's done, so that we can proceed with the actual parsing. So the initial thing was only the setup of parsing. Some 2 thumbs ups. Awesome. Okay, so once this is done, we'll proceed with parsing. And over here, I'm just using VASP. So VASP is one of the things that I use for periodic systems or materials, metals, and all the surfaces kind of stuff. So if you need to look at VASP, it's a paid version though. It's not a free to use version. But the files can be created. The files that we are going to analyze is something called XML files. So this is very different from a regular text file that other softwares produce. So I'm going to show you how to do that for this. And if you want to look at the files, you can just go to VASP and you will see the VASP XML file. So this is the XML file that we are going to pass for and show how it's done. And before writing any code, what I recommend you to do is to look at the parsers that are already available. so that you need not code from the scratch. So to run this, we'll look at how it's done. So this is the import command, which fetches you the things that you require, and then we'll just pass in this thing, which is the location of the file. So you would need to do something like this for all parsing, which says where the file is located, and this is where the file is located. And you can run it. Fatal error. So if you see a fatal error, so let me show you when that happens. So if you try to run it again over here, it'll show you a fatal error, which says parsing already exists. In that case, what you need to do is just click on these things that you see at the side, and you will see the parsing files. And that is the reason it says that this thing already exists. So what you can do is just click on these three dots and rename the folder to something else, maybe ABC or something, and then click, then try to get it. It should be able to get it. So there's another question. Could you please tell how to get to the collab? Okay, so getting to the collab is you need to go to this GitHub page of mine. And once you go to that page, you will see a file which is called parsing files. Click on that parsing files, and then there'll be a blue thing on top over here, open in Colab. Just click on open in Colab. It should open you this file. So yeah, so once that is done, once you see all of that, so we are going back to parsing. So we'll just read in the file over here, and it reads in the file. And to see what things we can do with the files being read, there's this method in Python there's this function called dir, which tells you what all things you can do with this. So it'll show you all those things like actual K points. If someone has done periodic calculations, you'll know what K points are, and whether the thing has converged, whether the quantum chemistry calculation is converged. You will get the energies and all of that. So you press this, you'll see a lot of things in here. And as this is interactive, I encourage you to open the book and click on those buttons and see what you get. So you can change the things around and play around with that. It's not going to change the code on my side of it. So you're fine doing it. Okay. So in this calculations, we'll see whether the thing has actually converged, and it says it's converged. The QM calculation is converged. You can also get the final energy from the structure from the file, and this is how the final energy is got. So all of these would be available when you just say when you just use this function dir, and the thing that you created with that, it'll show you all those things that are available. So this is all just demonstrating what all things you can do with it. So, and then you can even do something called density of states. So if you want to know what density of states is, you can just look at this thing. There's a link for Wikipedia, which gives you more information about density of states. But you can just go ahead and plot this from the file that we just passed, and you'll just see a figure which is the density of states. These are densities, and this is the Fermi level and all that stuff. So the point that I want to drive home is you can use all these things that are already existing to parse your own code instead of parse your files, instead of writing your own code to do stuff. And they do have some things like plotting them within the code. So please do look at pymatgen when you're thinking of plotting. Okay. So while the thing that we first did was an XML file, it's a very different file. You can't just open it. If you want to open the files over here, you can just go to the files and then VASP, and I think OUTCAR would open. So you can see OutCar opens for me on this side. So just click on it, it opens because it's a text file. And I'll show you how to parse text files too. Okay. So XML being a different file, it won't open up. It'll ask you to download it. So it'll ask me to download it. So it's okay. So that's one reason why I showed you how to do those files. So there's OutCar file, you can do the same. And in this, what we're trying to get is the one stat. And I'll show you what it's actually parsing. So if you go to this file and the bottom of that file, so at the bottom of this file, this is what we are trying to get, is this one, this information. What is the average memory used and all of that. So it parses that thing. Okay. So this is a text file which is used for parsing. So any questions so far on how to use the parsers that are already available for at least materials chemistry code? So were you able to run those cells and see the output? Yes. Okay, awesome. So we'll go into parsing Gaussian files. This is for molecules, and we'll still use the same thing for parsing. And over here, I give you a link for pymatgen, which on clicking, I'll show you what it does. So if you click that link over here, pymatgen, it'll show you what all it can parse. So if you go to the bottom, so you can parse Babel, you can parse cube files, you can parse Jarvis, you can parse PhononPy. There are a lot of these things, and there's NWChem if someone wants to parse it. We are using the Gaussian one, and there are other packages too over here. You can parse QChem, you can parse Lobster, there's Labs, there's Exciting, there's CP2K, Abinet. So these are all the things that you can parse with pymatgen. So if you want to parse any of these files, do look at pymatgen before writing your own parsing. And I'll show you at the end of this how we can write our own parsers. Okay. So for Gaussian, we'll use this, and then we'll say import Gaussian. So just click this so that we get all the libraries that are needed, and the Gaussian file is located here. So if you want to look at it, just click on Files, go to Gaussian, and there's tddft.log. And this is a tddft calculation. It's time-dependent density functional theory, and you can look at it. You can look at more of it at Gaussian and see what it means actually. But it gives absorption and all that kind of things of a molecule. So again, you can click on dir and see what things are available for this. So you can get the final structure. You can get all those excitation energies and all of it. So that is what we are going to do over here. So at first, we are going to get the final energy. And this is the final energy of that molecule. So you can look back at the file and see what is the final energy and whether it matches it. And then you can see what is the final structure. So you can get the structure or the optimized structure from the calculation that you just ran. So can we email you questions? There's a question which says, can you email you our questions if we have later? And it's possible to have a copy of recording. So this thing will be made available on YouTube because this is recorded, hopefully. And you can look at the YouTube videos. The code will be still there at the links that I shared with you. And if you have any questions, you can just type it as a comment in the YouTube video, and I'll try to answer it. So if that works. Awesome. So yeah, so you can get the molecules and you can get energies, very much similar to the things that we did earlier. Okay. So, and you can also read the tddft excitation energies from here. And these are these excitation energies. Did you keep TDFT file in Gaussian folder? There's a question which asks, did you keep the TDFT file in Gaussian folder? Yes. If you want to look at the TDFT file, you can go to the Gaussian folder and you can see the TDFT file over here. And this is the TDFT file. And from there, if you go down and see the excited states, and it's parsing these excited states over here. So you can see 3.4722 is this energy, and then we have 356, which is that. The second is 4.55, and you can see all of those being passed automatically. So you can just open the file and look at it. The thing that we are trying to do is, just given a file, can we just get things out of it directly instead of scrolling up and down and finding how to get those values. Okay. So any questions so far on using pymatgen for just generate things like this? So the next part that we'll try to spend time on the next hopefully 15 to 20 minutes is how to write parsers ourselves. So this is the first introduction was to use the parsers that are already available, which people have written, and we'll now try to generate parsers ourselves. There's a question. So we use the same script pymatgen for all of these functions. We use pymatgen, the package, but for this we use something called Gaussian output. This is a different set of code. And then at the top, if you go scroll up, we use a different parser for VASP. It's called VASP1. So they use different functions, but it's still the whole package is pymatgen. There are other packages which you can use. There's something called ASE. Excuse me. So there's something called ASE you can use to do all of that stuff. Okay. So let's go into parsing ourselves. Okay. So let's start. Where is it? Where did I go? Okay. So this is for text files. Okay. So all of this will be done for the text files. For other files, it will be more complicated. But the thing that I'm going to show you how to do it yourself for any file that you have. It's not only limited to computational chemistry file. You can do it for any file that you can think of. Okay. Any text file. So for that, we use something called regular expression. Can you still see my screen? With generic parsing? Yes, okay, awesome. So we will use something called regular expression. And if you want to know more about it, just click on this Wikipedia link and you'll find more about it, how to do it. Sorry. So the thing is, you want to find a unique pattern, okay? So the regular expression does that. It finds a pattern for you and it tries to match a pattern that tries to find a pattern for you, and you can use that pattern to parse the things that you need. For example, if you wanted to parse these excited states that you see over here, all that you would need to do is find this pattern of excited states, and then whatever follows it is a number, and then you can say, okay, this is how I parse the states, okay? And so this is the procedure that we would go through, okay? So at first, what you need to do to parse a thing is to look for pattern, okay? We need to look for pattern. So is it, okay, so there's a question, is it must to install pymatgen for every login into Colab? So yes, excuse me for a minute, I'll just make some. Okay, yes. So if you log in to Colab again, it'll ask you to install the thing again. So every time you open Colab, it'll ask you to install it. So yes, you would need to install it. Okay, so back to what we are trying to do over here is to find a unique pattern that we are going to start parsing with. And then once you find the pattern, you need to find where we need to start and where we need to end. And then once you have that, you can read the file, look for the line pattern and all of that. So this is what we are going to do, and I'll show you how it's done so that you can try it yourselves. And what we are going to pass, we are going to pass these from the ttdft log file. So you can open it from the files over here, ttdft.log. And what I want to show you to pass is this part over here. Okay, so we'll try to pass the Mulliken charges. Okay, you can use it for anything, but as an example over here, I'm trying to show you how to pass Mulliken charges for this. So at first, we'll try to import this regular expression thing in Python. It's called RE, and we'll just click on it. It'll import it. Okay. And if you're trying to do this part, there's no need of installing pymatgen because we are doing it without pymatgen. So we can just go ahead and use this part. So just import RE. And now we need to find the start pattern for this. Okay. So if you look at this, the start pattern is Mulliken charges. That's where you want to start parsing the files. Right. So we want to parse it from here all the way until here. Right. So we want to start from where it says Mulliken charges. So we'll use this something called compile, and we'll say the start pattern should contain Mulliken charges. So this is where we're going to start. And the syntax is something like this, which needs an R and then pass what you want to match the start with. Okay. And the end pattern should contain something like sum of Mulliken charges. And we say sum of Mulliken charges should be the end pattern that we want. Okay. Any questions so far with this? So we are trying to pass this part from the file of tdft.log. We want the charges on each atom. And this is the start pattern. We put that as a start pattern and put this as an end pattern to pass. So any questions so far at this point, something that you did not understand? Is everyone able to see, everyone able to do this until this point? So that I know it's working for you guys. Okay, it's working. Okay, so we'll start and compile this. So we'll say this is the start pattern and the end pattern of the file. So we need to start from here on the tdft Mulliken charges, and we need to end at sum of Mulliken charges. So once we do that, we'll then try to read files. And what I prefer to do is read each of these files as a list. Okay, each file will be a list so that you can just say where, or you can just loop over that. Okay. So these are some Python terms that I'm trying to put in there, but you'll see how that is done. So once you do this lines, you can check what type of a variable lines is. So you can just run this cell and it'll tell you what it is. So it'll say that the lines that we did right now, this is the reading of the file. Okay, we read the file, and the thing is, this is a list, and these are the entries in the list. So the first line is this, the second line is that, and between the commas is what the lines are. So if you just scroll top of this file, you'll see the first line is entering Gaussian system, and then second line is input, so on. So over here you can see up to 10 lines that are printed from this file. Okay, and that's we have done the first three things. How can I keep my own file inside a Gaussian folder to do parsing? So if you have your own file that you want to parse right now, what you can do is you can just click on this upload button, and it will upload it to the storage over here. and it'll probably put the file somewhere below sample data. And then what you can do is you can just drag the file inside Gaussian folder if you want, or just keep it outside in the content folder. So in that case, if you want to know where the file is, for example, you need to, how did I get this thing, right? So I said, I need to put in this, and the way I get it is just click on, just right click on that and say copy path. And the path that is copied is actually the path where the file is located. So if you want to do some parsing of your own, what you would do is just upload the file here and whatever file you're working with, and it will be uploaded, and just right click on it and copy path, paste the copy path onto this file, and it will open the file for you. I hope that helps. Someone is doing parsing on their own. So yeah, back to, oops, I think I closed the file. Okay. So we did read this file, okay? And where are we? Parsing, okay. We are at this state where we have Mulliken charges, and we see we have read all the lines as a file, right? So what we now do is we need to find where this Mulliken charges exist, right? So we need to know the line number of this. So it's not always on line 1402. It may change depending on, this may change depending on where you, how many atoms there are in the molecule and all of that. So we need to find out where this Mulliken charges exist. So if we use this match function from RE, what it does is it tries to match the pattern. So we want to find out where this line exists. So we say, can you match this pattern for the line? So if that exists, it will say this is true, and it will just break the loop, and we'll know what the index of what is the number of this file, what is the number of the line where you see Mulliken charges, or the start pattern in the file. So we just say line.strip, and we try to match it. So we loop over all the lines above, and only when it is succeeding in finding this pattern, it will print out the index first. Okay. So if you just run this file, you will see it says that the start pattern was, which is Mulliken charges, and you can see that from here, the start pattern exists at line 1401. The reason it says not 1401 and not 1402 is Python starts with index of 0. So the first line will be 0. So because of that, we see one number less than the number that is shown over here. Okay, so this is the way to test that, yes, we can get this line, which is Mulliken charges, and the index for that line is 1401, which will be less than the actual line number that you see. Okay. So any questions so far? How do you get the start? How do you get the line that contains the start pattern? And how do you read the file or use the start pattern to do it? Any questions? You can unmute yourself and ask me questions if you want, or you can just type it in the chat. Is there a module that can pass the geometry in XYZ or Gaussian? Is there a module that can pass the geometry in XYZ or Gaussian files, also pass the basis set, for example? So if you look at the Gaussian thing that we did on top, there are a lot of things in this Gaussian module, and you can actually say, where is it? Okay, so once you do this, there is way of the basis set. So you can see there's something called basis set here. So if you just use gout.basis set, you will see the basis set that was used for this this file. And if you want to save the final structure, I just showed you how it's generated, how it looks like final structure. But if you look at the commands, if you do dir on this, you will see what all you can do with this thing. And then, so there's this function called to, and if you look at what this function to does, is what it saves the file. It saves the coordinate as XYZ geometry. So you can save the XYZ files. I can show you an example later, but I would strongly encourage you to look at this, and then it will save the geometry as XYZ. I hope that helps. So there's a question, can we view the Python code that does all of this? Yeah, I can show you at the end how to look at the code that does all of this. So let's get back to the generic parsing part so that I can give you some time to work on other things yourselves. So any questions so far until as to how you're going to find the start pattern of the file or something like that? Okay. So this is the process that we are following. We try to find a unique pattern. We try to find an end pattern for the segment. We found both of them. We read the file, and we started looking for the start pattern of the file and to find the line that contains the start pattern. And we found out that line 1401, which is index with 0, so it should be 1402, contains that thing. So we need to start parsing the data. So in this case, we'll start parsing the data, but we don't want this one that is printed in here, right? So we want only these things. So I say index plus 2, because the current index is this. I want to skip this. I want to skip this. So I'll start with line 1404. And in that case, it'll be 1403 when I say index plus 2 over here. And then for all that pattern, what I'm going to do is I'm going to continue adding those lines to parsed lines and then increment the index. So once I start with the 1403, which will be this line, it'll get this line, and then index will be increased. So it'll become 1404, and it'll take this line, and that goes on. Okay, so that is what we are going to do. And in the end, the parsed files should have the data which is between this, the Mulliken charges and the sum of Mulliken charges. Okay, so we do need to use the strip so that we clean up the empty spaces and all of that at the end of the file. Okay, so once you run this you will see, I'll just show you the printed lines, and it'll show you the first thing that you saw here, which was 1C minus 4 minus 0.465 and so on. So you'll see all of those being printed here. Okay, they're all of those. So you can go ahead and clean this up so that it is in the form of the number, the atom, and then the charge. So if you just take the first line and see what it looks like, it is like that, right? So you have a number, you have a C, and then you have a charge. So if you want to put that in a nice form, right, which is something like this, atom C, atom number 1, atom C, and all of this, you can just use this code. This is just modifying so that it looks nice. There's nothing great about this part, and I'll just show you what it looks like, right? So we just used the first line, which looks like this, and transformed it into something like this. It's just nice looking. And over here, this are if you go into the details, this is a string, but we converted into a float. We typecasted integer so that it's easy to work with. Okay, and then this is just for one line. We can do it for all the lines, and this is what we can do it for all the lines. And over here, I just use pandas data frame. This is one thing, and you can see we pass the entire data into a pandas data frame. You can save this as an Excel sheet if you want and use it somewhere. So this is a way of having nice data, right? So you can see over here, it's 1C and this. So you have number, atom, and charge. You can see all of those being passed until the end, which is 52. And you would see at the end 52, right? This is the index thing, so it'll be 50. It starts from 0, but 52 H and all of that. So this is how you are going to parse a generic text file. You can apply this approach for any file that you want to parse. And all you need to do is find the start pattern, end pattern, read the file, and apply the same thing. You can reuse this code that I've shown here to anything that you want. Only thing that you would need to change is what is your start pattern and what is your end pattern. And in between, you'll get all of these lines. Okay. Any questions so far on this? So we almost got it on time. So this is an example exercise for you to do. So you can try it out yourself. So the thing that we are trying to do now is to take these parts over here. So can you parse these charges which are below? So it says Mulliken charges with hydrogen atoms. Can you try to parse these and put it in a nice data frame if you want? So this is an exercise for you to do, and you can work on this right now, and we'll be here till 11. So you have ample time to work on it and ask me questions if you have any so far. Is it possible to extract data from multiple files? There's a question which says extract data from multiple files. Yes, you can do that, but if you want to extract multiple data from if you want to extract data from multiple files, what you would need to do is parse one file at a time. And that's how you could do it. As long as you have something like a list of lines or something, you can try to mix and match things and then say, okay, you want to match this with, you want to match the start pattern that you see here and find another start pattern in the other file and start merging things together or something like that. Even that is possible, but one file at a time is the most easiest thing to do. But the thing would be the same, right? So find the start pattern, find the end pattern, and read the file, and then try to find where the start pattern, the line that contains the start pattern, and then start parsing until you reach the end pattern. So, okay, so there's another question. Could you please show us how to extract HOMO and LUMO gap? We could write a code to extract that, and the HOMO LUMO gap actually lies here, right? So these are the orbitals, and from the orbitals, where is it? Okay, so you want the difference between this orbital over here and that orbital over here. So that is the HOMO-LUMO gap, and this is the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital, and the gap between them is what you need to find. We can write a code, but that code already exists in Gaussian. So what I would do is, I can quickly show you that part. So let's say HOMO-LUMO. So if you remember, G out had everything, right? So G out had that file. So there's something called energies, I think, eigenvalues. So if you look at these are the eigenvalues that you see over here. Okay. So these are the eigenvalues, and it gives you the eigenvalues directly. So if you look at the last one, hopefully it'll be the last one that you see here. So let's see. So as you see here, so this is the last eigenvalue, 40905 and 40, all of this. So pymatgen does it for you, all of these eigenvalues. So now the only thing left is how to get the HOMO-LUMO from there, right? So HOMO is the number of electrons divided by 2 will give you the HOMO value. So I think this has something called N. Electrons. So there you go. So you have 99 electrons in this. So sorry, 100 electrons in this. So it gives 99 because it's index 0 to 99. So there are 100 electrons in this. So the orbital 50 is what you're looking for. So 100 orbital 50. Yeah. So if you look for eigenvalues of what is that, 50 or something, I think 49 maybe, because it's index 0. So eigenvalues is a list. So I'll just do dot values. So if you do something like this, values. Okay. So if I do something like this, it's converted into a list, and then if I get the 49th value from here, I hopefully should get where is that? 0. It's all indexed like that, so then you can do 14. Where did that go? So yeah, so this is all indexed, and if you look at the electrons divided by 2, you should get the value of HOMO, and where's that? Okay, alpha virtual, alpha this. So we need this value. I think it's 50. Where did we go? Oh, sorry, 99, right? So yeah, so it should be 98. So there are 98 and 98 electrons. So that's what we got from electrons over here. So then 98 would give you that value. So if you want the HOMO-LUMO gap, the difference between 98 and 99 will be the HOMO-LUMO gap for you. And this is in Hartree, so you can convert it into things. I hope that helps. So there's another question. Is there any similar strategy to create input files for such simulations, in particular LAMs, VASP, LAMs, and Gaussian? So I would strongly encourage you to look at pymatgen. So pymatgen has ABINET, CP2K, LAMs. If you're interested, there's ways to generate input, there are ways to generate output. So if you want to do your own thing, I would strongly recommend you to look at this and see whether the code exists before writing your own parsers. So there's Gaussian, there's QChem, there's VASP, and VASP is what I showed you in the earlier part of this file over here in this parsing thing that we did. So yeah. Okay, cool. So there's another question. Didn't know we could create inputs. Yes. So I just showed you creating outputs. Creating inputs depends on how your other files are. If you can use XYZ file or something to create it, you can use a POSCAR, you can use a all of those things. So I didn't go into those specifics. Over here, the idea was how to parse the output files. So you can definitely create the input files for those softwares too with these things. So Gaussian, if you go to Gaussian can create you the input file given a molecule, and then you can say this is the charge multiplicity that I want. It'll write you a GGF file or a .com file. So you can create the input files for these soft codes as well with using pymatgen. It's a really cool package that they have built. So was anyone able to go through this exercise thing? Hopefully, if you have any questions, I would answer them. So there was another question which I skipped, which was, can we view the Python code that does any of these functions? So all you can see that these functions that we used, which was maybe eigenvalues, the final structure, final energy, how do they actually work, right? So if you just hover over this, hopefully it does. Does it do it? So yeah, so if you press Control and you will see that blue line on there. So once you click on that, you will see the source code for that file. So it says final energy is -1, and then you'll go see, you need to go and see what these energies are. Then just click on this variable, and then you'll go back to the code that goes on behind all of this. So you can see all the code, how coordinates are passed, how molecules are passed, how the input structure is passed, and all of that. So all you need to do is press Control and see that blue line thing, and just click on it. It'll show you the code for all of it. For example, if you want to go to maybe parsing code itself, if you want to go to this plotter code, so just click on this. You'll see a blue line and click on that. It'll open the plotter code for you. So this is the code that is being used while we are running this. I hope that helps. So there's another question. Shall use this GitHub stuff in Anaconda? So if you want to do Anaconda, all you would need to do is install pymatgen. The code will be very much similar, which will be pip install pymatgen, and it should be able to do it. If you want to do the generic parsing, the regular expression would be installed by default, I think, because it's a Python. It comes with Python these days. So the regular expression RE should also be there. So you can you can even open these files with with Jupyter Notebook and Anaconda, or you can just use a Python file and just type in your code and copy paste these things. I hope that helps. Any more questions? So we have 1 more minute before we end. So again, if at the bottom of this is a survey link, so please take this survey and do let me know what you think about this workshop, and your feedback would be very helpful for me in creating more content for the next workshop and improve the way it's delivered. Okay, I'll probably go ahead and stop the recording.